Welcome. Today, we'll explore LeetCode problem number 1243, Array Transformation. This problem challenges us to apply a series of transformation rules to an array until it stabilizes. We'll walk through the solution step by step, discuss the algorithm, and analyze its efficiency. Let's dive in. In this problem, you're given an integer array called ARR with n elements. Your task is to perform a transformation on the array following a set of specific rules. If an element ARR I is greater than both its neighbors, ARR I1 and ARR I plus 1, it decreases by 1. On the other hand, if ARR I is smaller than both of its neighbors, it increases by 1. For all other cases, the value of ARR I remains unchanged. These transformations are applied repeatedly to the entire array until no further changes occur in a complete pass. Once this condition is met, the final state of the array is returned. The input to the function is simply the array ARR, and the output is the transformed array after all the changes are completed. For example, consider the array ARR equal to 6, 2, 3, 4. During the first pass, the second element, ARR1, increases to 3 because it satisfies the condition where ARR0, ARR1, ARR2. After this change, no other elements in the array meet the transformation rules, so no further changes are made in subsequent passes. The transformation process terminates, and the final array is 6, 3, 3, 4. Another example is the array ARR equals 1, 6, 3, 4, 3, 5. Here, in the first pass, several transformations occur. ARR1 decreases to 4 because ARR0, ARR1, ARR2, ARR2 increases to 4 because ARR1, ARR2, ARR3, and ARR4 increases to 4 because ARR3, ARR4, ARR5. After these changes, a second pass is made, but no further transformations are needed, so the process stops. The final array is 1, 4, 4, 4, 4, 5. Now, consider the array ARR equals 1, 2, 3, 4, 5. Here, no elements satisfy the transformation rules because no element is greater than both its neighbors or smaller than both its neighbors. As a result, no changes are made during the transformation process, and the array remains 1, 2, 3, 4, 5 even after repeated passes. This demonstrates that the algorithm correctly identifies when no transformations are necessary and terminates accordingly. In all cases, the process ensures that the output array is the unique result of applying the transformation rules iteratively until no further changes are possible. The problem also comes with some constraints. The length of the array, ARR length, is guaranteed to be between 1 and 10,000, and each element of the array, ARR I, will be a non-negative integer between 0 and 10,000. It's important to note that the transformation rules only apply to the elements in the range 1 to n2, meaning the first and last elements of the array are never modified. Additionally, the transformation is applied iteratively to the entire array until no changes occur during a complete pass. Since the rules ensure a strictly decreasing number of changes with each iteration, the process is guaranteed to terminate, and the output array will always be unique for any given input. These constraints ensure that the problem is well defined and can be solved efficiently even for large input sizes. When tackling problem number 1243, array transformation, the essence of the task is to repeatedly apply specific transformation rules to the array until it reaches a stable state where no further changes occur. One straightforward approach to solve this is through a brute force iterative simulation. The intuition here is simple. For each non-boundary element in the array, we follow the transformation rules. If an element is greater than both its neighbors, we decrement it. If it is smaller than both its neighbors, we increment it. This process is repeated round by round until a full iteration passes without any changes. To implement this, we can use a temporary array to store the updated values for each round, comparing it with the original array to check if stabilization has been achieved. While this method is easy to understand and directly mirrors the problem's rules, it has some limitations. Specifically, the time complexity can reach n squared in the worst case, as we may need many iterations for the array to stabilize, and the space complexity is n due to the additional array. This makes the approach less efficient for larger input sizes, but it remains a conceptually simple starting point to understand the problem dynamics. A more efficient alternative is the in-place simulation approach, which eliminates the need for a temporary array. Instead, the array is modified directly, and we use a flag to track whether any changes occurred during an iteration. If no changes are made in a complete pass, the array is stabilized. The implementation involves iterating through the array, applying the transformation rules directly to each element, and updating the flag if any adjustments occur. This process is repeated until the flag remains false. While the time complexity remains O(n squared), in the worst case, this method is more space efficient, requiring only O(1) additional memory. This improvement makes it more practical for larger inputs. Another alternative worth considering is the monotonicity analysis approach. The transformation rules imply that the array will eventually stabilize into a monotonic or uniform state. By analyzing the patterns of increments and decrements, it might be possible to predict the stabilized array without simulating every step. However, this approach is theoretical and involves deeper mathematical analysis, making it less general and harder to implement. While it could potentially achieve O(n) performance, its complexity and limited applicability are significant trade-offs. Among these approaches, the in-place simulation method stands out as the most balanced choice. It provides a good compromise between simplicity and efficiency. Although its time complexity remains O(n squared), similar to the brute force approach, it avoids the additional space overhead of using a temporary array, making it more suitable for larger inputs. There are a few key observations that make this approach effective. First, only the elements surrounded by larger or smaller neighbors are affected by the transformation rules, meaning boundary elements remain unchanged. Second, the transformation rules ensure that the array stabilizes over time by reducing local peaks and valleys. Finally, using a flag to track changes allows us to stop iterating as soon as no further updates are needed, eliminating unnecessary computations. This approach does sacrifice some readability compared to the brute force method, as modifying the array in place can make the logic slightly harder to follow. However, the reduced space usage is a worthwhile trade-off. The realization that only local changes matter, combined with the use of a flag to optimize iterations, was a key insight that solidified this method as the chosen strategy. Overall, this approach ensures correctness, minimizes memory usage, and provides a practical solution within the given constraints. To solve the array transformation problem, we need to repeatedly apply a set of transformation rules to an array until it stabilizes. Let's break it down step by step. First, the transformation rules. For each middle element in the array, if the value is greater than both of its neighbors, we decrease it by 1. If it's smaller than both neighbors, we increase it by 1. Otherwise, the value remains unchanged. The first and last elements of the array are special cases and remain constant throughout. Next, we initialize key variables. We create a copy of the input array called new_array, which will hold the transformed values. This ensures that updates during the current iteration don't interfere with each other. We also use a Boolean flag called change to track whether any transformations occurred in an iteration. If no changes happen, it means the array has reached its stable state, and we can stop processing. Finally, we implement an iterative transformation process, where we keep applying these rules until the array stabilizes. Now, we start the iterative process. At the beginning of each iteration, we set the changed flag to false. Then, we loop through the array, focusing only on the middle elements, those between the first and last positions. For each of these elements, we apply the transformation rules. If the new value for an element differs from its current value, we update it in new_array and set change to true. This signals that the array isn't yet stable and another iteration will be needed. Once we've processed all the middle elements, we copy the contents of new_array back to the original array A, preparing it for the next iteration. The loop continues until changed remains false, meaning no further updates are needed and the array has stabilized. At this point, we return the stabilized array as the final result. This iterative simulation works effectively because the transformation rules are local, meaning each element's value is influenced only by its immediate neighbors. With each iteration, the array moves closer to stability as the changes gradually decrease. Stabilization is guaranteed because each element has a finite number of possible values, and with every iteration, the array either decreases, increases, or remains unchanged. Eventually, the process terminates after a finite number of iterations. When considering edge cases, arrays of length 1 or 2 don't undergo any transformations since there are no middle elements to process. Similarly, arrays with all identical elements or strictly increasing or decreasing sequences will stabilize quickly, as there are no conflicting neighbor relationships. To implement this, we use a few essential data structures: the input array A to track the current state, a temporary array new_array to store the transformed values, and the Boolean flag changed to monitor whether any updates occurred within an iteration. The efficiency of this algorithm comes down to the number of operations performed. Each iteration processes all the middle elements in the array, applying the transformation rules in constant time for each. This results in a time complexity of O(n) per iteration, where n is the length of the array. In the worst case, the array may require O(n) iterations to stabilize, such as when dealing with zigzag patterns where elements alternate between increasing and decreasing. This leads to an overall time complexity of O(n) squared in the worst case. Space complexity is O(n), as we use the temporary array new_array to store intermediate results. To make this process clearer, let's look at the pseudocode. We initialize the length of the array, create a copy for new_array, and set the changed flag to true. The while loop runs as long as changed is true, ensuring that we continue transforming the array until it stabilizes. Within the loop, we iterate through the middle elements of the array. For each element, we check if it's greater than both its neighbors. If so, we decrement its value and mark changed as true. If it's smaller than both neighbors, we increment its value and again set changed to true. If neither condition is met, the value remains unchanged. After processing all the middle elements, we copy the contents of new_array into the original array A to prepare for the next iteration. Once the array is stable, we exit the loop and return the final result. There are also opportunities for optimization. Instead of copying new_array back to A after each iteration, we can alternate between two arrays to avoid unnecessary copying. Additionally, by leveraging the changed flag, we can terminate the process early if no updates occur during an iteration, saving computational time. These optimizations help make the algorithm more efficient while maintaining its correctness. The provided solution implements the transformation rules for the array transformation problem. The goal is to repeatedly apply these rules to stabilize the array. First, we enter a while loop to continue transformations until the array stops changing. Inside the loop, we create a copy new_rr of the array to track changes while preserving the original state for comparison. Then, we iterate through the array, skipping the first and last elements since they are not subject to transformation. For each element, if it is greater than its neighbors, we decrement it, and if it is smaller than its neighbors, we increment it. After processing all elements, we compare new_arr to the original ARR. If no changes are detected, the loop breaks. Otherwise, we update the array to the new state and continue. Finally, we return the stabilized array. This approach ensures a clear and efficient implementation of the transformation process. Here, we begin by importing the necessary Java utilities, and then we define our class and method. The method, transformArray, takes an integer array as input and returns a list of integers after performing the transformation. First, we convert the input array into a list called currentList. This conversion makes it easier to manipulate the elements during the transformation process. Next, we initialize an infinite loop to repeatedly apply the transformation rules until the array stabilizes. Inside the loop, we create a new list, which will store the transformed state of the array for the current iteration. To apply the transformation rules, we iterate through the elements of currentList starting from the second element and stopping before the last. The first and last elements remain unchanged. For each middle element, we check whether it is greater than its neighbors or smaller than its neighbors. If it's greater, we decrease it by 1, if it's smaller, we increase it by 1. This ensures that the transformation rules are applied consistently to all middle elements. After applying the transformation rules, we compare the new list with current list. If they are equal, it means the array has stabilized, and we exit the loop. If not, we update current list to reflect the changes in new list and continue the loop for the next iteration. Once the transformation process is complete, we return the stabilized current list as the result. This implementation ensures that the transformation rules are applied iteratively until no further changes are needed, and the final stabilized array is returned as a list of integers. In this problem, array transformation, we are given an array and asked to modify its elements based on specific rules until the array stabilizes, meaning no further changes occur. The transformation targets the middle elements, leaving the first and last elements untouched. Each middle element is adjusted based on its neighbors. If the element is smaller than both neighbors, it is increased by 1. If it is larger than both neighbors, it is decreased by 1. Otherwise, it stays the same. Let's look at an example to better understand this process. Starting with the input array 6, 2, 3, 4, we initialize by copying it into new_rr as 6, 2, 3, 4. For the first iteration, we check each middle element. At index 1, the element 2 is less than both of its neighbors, 6 and 3, so we increase it by 1, resulting in new_rr, 1, equals 3. At index 2, the element 3 is between its neighbors, 2 and 4, so no change is made. This gives us the updated array, 6, 3, 3, 4. Since the updated array differs from the original, we continue to the next iteration with arr equals 6, 3, 3, 4. In the second iteration, we again evaluate each middle element. For the element at index 1, which is now 3, it is not smaller than its neighbors, nor is it larger than both, so no change is made. At index 2, the element is also 3, and the same reasoning applies, no adjustment is needed. The result of this iteration is 6, 3, 3, 4, which matches the previous array. At this point, the array has stabilized since no further changes occur. The output for this example is 6, 3, 3, 4. This demonstrates how the transformation process halts once the array reaches a stable state where all elements meet the specified conditions. Next, we'll explore an example where the array undergoes more iterations before stabilizing. Now consider the input array 1, 6, 3, 4, 3. As before, we initialize by copying it into new_rr. In the first iteration, we evaluate each middle element. At index 1, the element 6 is larger than both of its neighbors, so we decrease it by 1, making new_rr, 1, equals 5. At index 2, the element 3 is smaller than both of its neighbors, so we increase it by 1, resulting in new_rr, 2, equals 4. At index 3, the element 4 is larger than both of its neighbors, so we decrease it by 1, giving new_rr, 3, equals 3. The updated array becomes 1, 5, 4, 3, 3. Since this differs from the original, we proceed to the next iteration. In the second iteration, at index 1, the element 5 is still larger than its neighbors, so we decrease it by 1, making new_rr, 1, equals 4. The element at index 2 remains unchanged because it is between its neighbors. Similarly, the element at index 3 also remains unchanged. This gives us 1, 4, 4, 3, 3. In the third iteration, all middle elements meet the conditions for no change, so the array stabilizes as 1, 4, 4, 3, 3. This example highlights how the array can oscillate through several iterations before reaching stability. Finally, let's examine a case where no changes are needed. Take the input array 1, 2, 3, 4, 5. After initializing, we evaluate each middle element in the first iteration. At index 1, the element 2 is greater than its left neighbor but smaller than its right neighbor, so no change is made. At index 2, the element 3 is similarly between its neighbors, so it remains unchanged. The same applies to index 3, where the element 4 is between its neighbors. The result of this iteration is 1, 2, 3, 4, 5, which is identical to the original array. Since no changes occur, the array is already stabilized, and the output is 1, 2, 3, 4, 5. This example demonstrates that an array already meeting the conditions will stabilize immediately without any transformations. Key takeaways from these examples are that the transformation is driven by comparisons with neighbors, the process halts when no changes occur, and the edge elements always remain unchanged. The time complexity of the transform array function is determined by analyzing two main components, the outer while loop and the inner for loop. First, the while loop runs until the array stabilizes, meaning no further changes occur. This stabilization process depends on how many iterations it takes for all elements to move closer to their final values. Since each element can change only a limited number of times, bounded by the difference between the maximum and minimum values in the array, the number of iterations, denoted as k, is finite. In the worst case, k is proportional to the range of values in the input array. Next, within each iteration of the while loop, the inner for loop processes two elements of the array, as it skips the first and last elements. This gives a time complexity of O(n) for each iteration of the while loop. Combining these two parts, the overall time complexity becomes O(k*(n), where k is the number of iterations required for stabilization and n is the size of the array. If the range of values in the array is large, k can grow significantly, increasing the overall runtime. Now, let's discuss the space complexity of the transform array function. The space usage primarily comes from three components. First, the input array ARR is modified in place, meaning no additional memory is allocated for it. Second, a temporary array called new_RR is created during each iteration to store the transformed values. This array has the same size as the input array, which contributes O(n) to the space complexity. Finally, a few auxiliary variables, such as the loop index I and other control variables, are used. These require a constant amount of space, or O(1). Combining these factors, the overall space complexity is dominated by the temporary array, resulting in O(n) space usage. Let's compare this approach to potential alternatives and analyze the best, worst, and average cases. The current implementation is already optimized, as it efficiently applies transformation rules to adjacent elements without unnecessary comparisons or additional data structures. A naive approach, on the other hand, might involve comparing all pairs of elements or using extra auxiliary storage, leading to higher time and space complexities. In the best case, the input array is already stabilized, meaning no changes are needed. Here, the while loop runs only once, resulting in a time complexity of O(n) and a space complexity of O(n). In the worst case, the stabilization requires the maximum number of iterations, which happens when the range of values in the array is large. This leads to a time complexity of O(k*(n), where k is the number of iterations, but the space complexity remains O(n). On average, most arrays stabilize in fewer iterations than the worst case, so k is typically smaller. As a result, the time complexity remains O(k*(n), but with a smaller constant factor for k, while the space complexity stays at O(n). Finally, let's solidify the big O analysis with a mathematical justification. The time complexity arises from the nested structure of the while loop and the for loop. For each of the k iterations of the while loop, the for loop processes two elements, which simplifies to O(n). This gives an overall time complexity of O(k*(n). The value of k depends on the range of values in the array, meaning that as the range grows, so does the number of iterations and, consequently, the runtime. For space complexity, the dominant factor is the temporary array new_RR, which has the same size as the input array. This results in a space complexity of O(n), as the memory usage scales linearly with the size of the input array. These analyses confirm that the implementation is efficient in both time and space usage, given the problem constraints. When solving this problem, there are several common mistakes to watch out for. First, modifying the array in place during iteration often leads to unpredictable results because you're reading and writing to the same data simultaneously. Instead, use a temporary array to store the updated values for the next iteration. Next, boundary elements, which are the first and last elements of the array, need special attention. These elements do not change during the transformation, so forgetting to handle them correctly can lead to incorrect outputs. Another frequent issue is missing a termination condition. Without a proper check for when the array stabilizes, the program can enter an infinite loop, so always ensure that your loop ends when no further changes occur. Finally, comparing arrays inefficiently between iterations can slow down your solution. Instead of manually comparing elements one by one with a loop, use Python's built-in equality operator or similar methods in other languages for faster, more concise comparisons. Now, let's address some additional pitfalls and strategies. Ignoring edge cases can be a big issue. For example, failing to test arrays with all equal elements, single-element arrays, or arrays that are already stabilized might hide bugs in your solution. Always include these scenarios when validating your approach. From an interview perspective, this problem belongs to the category of simulations or iterative refinements. Recognizing this can help you quickly identify that auxiliary storage is often needed to save intermediate states. A key insight here is the distinction between in-place and out-of-place transformations, so be prepared to explain how your approach ensures convergence to a stable state. Interviewers might also prompt you to discuss optimization. While the naive solution is acceptable, you might be asked how to reduce space usage or streamline comparisons. Lastly, clear communication is critical. Make sure to articulate your stopping condition and justify why it guarantees the solution will terminate. Now let's look at related problems that can help you build a stronger foundation. LeetCode 73, set matrix zeros, is another problem where transformations require careful handling of auxiliary storage. Then there's LeetCode 289, the game of life, which involves similar rules where the next state of an element depends on its current state and its neighbors. LeetCode 54, spiral matrix, focuses on array traversal, particularly emphasizing how to manage boundary conditions effectively. Finally, LeetCode 832, flipping an image, is a variant of array manipulation with specific transformation rules. Practicing these problems will not only improve your understanding of array transformations but also enhance your ability to handle related scenarios in interviews. Let's explore some alternative approaches to solving the problem. One straightforward method is brute force with a temporary array. In this approach, you use an auxiliary array to store the transformed state during each iteration, then replace the original array with the new one. While simple to implement, this requires extra space. Another option is in-place transformation with indicators. Here, you mark elements in the array with special values during the iteration to avoid modifying elements that are yet to be processed. This method saves space but increases complexity and can introduce bugs if not carefully implemented. Lastly, you can optimize for early termination by tracking changes during each iteration. If no changes occur, you can terminate the process early, reducing unnecessary iterations. This approach minimizes iteration overhead but may require additional bookkeeping. Each method has trade-offs, so choose the one that best suits the problem constraints and your optimization goals. Great job! To wrap up, we discussed how to stabilize an array using transformation rules, the key takeaways, and some insights for similar problems. Don't forget to practice and explore variations of this problem to strengthen your skills. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!